vapor, liquid, solid phase, equilibrium in a pure substance, in a pure substance, consider as a system 1 kilogram of water contained in the piston cylinder arranging shown in this picture. Suppose that the piston and blade maintain a pressure of 1/10 megapascal in the cylinder and that the initial temperature is 20 degrees centigrade. As heat is transferred to the water, the temperature increases appreciably, the specific volume increases slightly, and the pressure remains constant. So we have, for example, in a constant pressure process, until slight motion. For example, heat transfer addition. When the temperature reaches 99 degrees, approximately, additional heat transfer results in a change phase as indicated in the B part in this picture. That is, some of the liquid become vapor, and during this process both temperature and pressure remain constant. So during the change phase, pressure and temperature remain constant from liquid to vapor. When the last drop of liquid has vapor, further transfer of heat results in an increase in both temperature and a specific value of the vapor, as shown in the part C. So when the last drop of the vapor liquid transfer to vapor, let me write it. Vapor. So further transfer of heat results in an increase in both in an increase in both temperature and a specific volume of the vapor as shown in the previous picture, part C. So we have, in this process, we have a definition for the term saturation temperature. Designates the temperature at which vaporization takes place at a given pressure. The term saturation temperature designates the temperature at which vaporization takes place at a given pressure, because this may be different in various pressure. This pressure is called saturation pressure. The pressure is called saturation pressure. For the given temperature. Thus, for water, for example, at 19 centigrade, the saturation pressure in 1/10 megapascal, and for water at 1/10 megapascal, the saturation temperature is 99.6 degrees centigrade. For a pure substance, there is a definite relation between saturation pressure and saturation temperature, a typical curve called the vapor pressure curve. The typical curve called the curve. Is shown in the picture here. The next page picture, we provide the picture for description. It shows the vapor pressure curve of a pure substance. If a substance exists as liquid at the saturated temperature and pressure, it is called a saturated liquid. If the substance exists as liquid at the saturation temperature and pressure, it is called a saturated liquid. Saturated liquid. If the temperature of the liquid is lower than the saturated temperature for the existing pressure, it becomes a subcooled liquid. If the temperature of the liquid at the saturation temperature and pressure for the existing pressure is called subcooled liquid, implying that the temperature is lower than the saturation temperature for the given pressure. And a compressor if the pressure is greater than the saturation pressure, for the given temperature, is called a compressed liquid. Either term may be used, but the latter term will be used in this book. There is also some definition which say that when a substance exists as part liquid, as part vapor at the saturation temperature, its quality is defined as the ratio of the mass of the vapor to the total mass. So we can write it when a substance exists as part liquid and part vapor, at the saturation temperature, its quality is defined as the ratio of the mass of vapor to the total mass. For example, in the part B, if for example the mass of the vapor, I will write with the mass of vapor equals 2 kilogram, and the mass of the liquid is 10 kilogram. The quality is total mass. M vapor to M total. In this case, it is equals to 2/10 or 20%. The quality may be considered an intrinsic property and has the symbol X. Intensive properties and is denoted by X. Quality has meaning only when the substance is in a saturated state. Means when substance is in saturated state. That is at saturated pressure and temperature. If a substance exists if a substance exists as vapor at the saturation temperature, it is called saturated vapor. Sometimes the term dry saturated vapor is used to emphasize that the quality is dry saturated vapor is used to emphasize that the quality is 100. Is 100%. When the vapor is at a temperature greater than the saturated temperature, when the vapor is at a temperature greater than the saturation temperature, it is said to exist as superheated vapor. As superheated vapor. The pressure and temperature of superheated vapor are independent properties. The pressure and temperature of superheated vapor are independent properties. since the temperature may increase while the pressure remains constant. Since the temperature may increase while the pressure remains constant. And actually the substance we call gas or highly superheated vapor. Consider this picture again. Let us plot the temperature volume diagram as this figure. This figure shows the temperature volume diagram, as also can be seen here. That represents the state through which the vapor passes as it is heated from the initial state of 1/10 megapascal and 20 degrees centigrade. This line. Let state A represents the initial state, this point, and B the saturated liquid state, in this case 99 and 6 degrees centigrade, and line AB process in which the liquid is heated from the initial temperature to the saturation temperature, A to B, this line. Point C is the saturated vapor. Saturated vapor point. And line BC is the constant temperature process in which the change of phase from liquid to vapor occurs, this line. Line CD represents the process in which the steam is superheated at constant pressure. Temperature and volume both increase during this process. Now let the process take place at a constant pressure of 1 megapascal, this line, starting from our initial temperature of 20 degrees, for example, the line E, point E, represent the initial state in which the specific volume is slightly less than that for pressure 1/10 at 20 degrees. Where precision begins at point F, where the temperature is approximately degree, the saturation. Point G is the saturated vapor state. This point at this specific pressure. And line GH is a constant pressure process in which the steam is superheated. This line. In a similar manner, a constant pressure of 10 megapascal is represented by line IJKL, for which the saturation temperature is equal to this temperature greater than previous and is 311.1 degrees centigrade. At the pressure, this pressure P equals to 4 megapascal, represented by line NO. We find, however, there is a no constant temperature vaporization process. Instead, point N is a point of inflection with a zero slope. This point is called the critical point. So, there is no constant temperature. Temperature and vaporization, constant temperature vaporization process. Instead, point N is a point of inflection with zero slope. Point N, this point is a point of inflection with a zero slope. This point is called critical point. At the critical point, the saturated liquid and saturated vapor states are identical. At the critical point, the saturated liquid and saturated vapor states are identical. Temperature, pressure, and a specific value. pressure and a specific volume at the critical point are called critical temperature, critical pressure, and critical volume. The critical point data for some substances are given in this table. A constant pressure process at a pressure greater than the critical pressure is represented by the line PQ at the previous picture. This table shows the critical temperature for water, carbon dioxide, oxygen, and hydrogen. Critical pressure and critical specific value, critical value. We are now should description the line PQ, which is above the critical point, this line. If water at, for example, 40 megapascal and 20 degrees centigrade is heated in a constant pressure process in a cylinder, as previous example, two phases will never be presented at the stage shown in the two-phase liquid and vapor never exist. So for the pressure greater than critical pressure, the pressure vapor state will never exist. Instead, there will be a continuous change in density. There will be a continuous change in density and at all times only one phase will be present. Only one phase will be present. The question then is, when do we have a liquid and when do we have the vapor? The answer is that it is not a valid question. At supercritical pressure, we simply call that the substance is fluid. However, rather than arbitrary at the temperature below the critical temperature, we usually refers to the compressed fluid. For compressed liquid for the temperature below the critical point. And above of the critical point we have temperature above critical is we have the superheated vapor. So let me write again. T is lower than T critical. We have compressed liquid, and for T greater than T critical we have superheated liquid. It should be emphasized, however, that at the pressure above the critical pressure, a liquid phase and a vapor phase of a pure substance never exist in equilibrium. Let me provide again the picture. In the temperature value, the line N, J, F, B in this line. FB represented the saturated liquid line, and the line NKGC is the saturated vapor line. And line NK saturated. By convention, the subscript F is used to designate a property of a saturated liquid of the, for example, by convention in the thermodynamics, the subscript F denote that the designated properties of a saturated liquid and the subscript G designated the saturated vapor the subscript G being used to denote saturated temperature and pressure, for example. Thus, a saturation condition involving part liquid and part vapor, such as shown in the cylinder example. Vapor, liquid in a cylinder and can be shown, for example, a TV diagram as below. This figure, all of the liquid present in a state F with a specific volume Vf is a specific volume for the liquid, and Vg, as we said, the liquid is the saturated vapor presented vapor specific volume The total volume is the sum of the liquid volume and the vapor volume is defined as V liquid plus V evaporation, and V equals to M, for example, multiplied to the specific value. We can write the relation there. V equals to M liquid plus M vapor Vg M liquid Vf M gas vapor Vg and also V on M. So if we divide the V on M, M liquid on M, M vapor on Vg, we have the relation X equals to M vapor on M. So 1 minus X is M liquid minus on M total. Substituting, we can write the V equals to F plus X Vg. Vfg can be defined as Vg minus Vf. So we can write Vf plus Vf minus X Vf plus X Vj plus X Vj minus Vf. With this definition, we can write the F plus X Vfg. Now the quantity X can be viewed as the fraction. We have also a definition for the quantity X. minus VF on VFG. Another definition, and also we have a vapor total. Let us now consider another experiment with the piston cylinder arrangement. Suppose that Let us now consider another experiment with the piston cylinder arrangement. Suppose that the cylinder contains 1 kilogram of ice and suppose that we have 1 kilogram ice at and pressure megapascal. When the heat is transferred to the ice, the pressure remains constant. The specific volume increases slightly and the temperature increases until it reaches 0, at which point the ice melts and the temperature remains constant. In this state, the ice is called a saturated solid. So let me write. When heat is transferred to the ice, the pressure remains constant the specific volume increases slightly and the temperature increases until it reaches until 0 degrees centigrade, at which point the ice melts and the temperature remains constant. In this state, the ice is called saturated solid. For most substances, the specific volume increases during this melting process, but for water, the specific volume of liquid is less than the specific volume of the solid. When all the ice has melted, further heat transfer goes on, increasing temperature of liquid. If the initial temperature changes to the another pressure, heat transfer to the ice results in an increase in temperature to, for example, another point as the ice starts to melting. At this point, however, the ice passes directly from the solid phase to vapor phase. This process known as the sublimitation point. Further heat transfer results in superheating of So if at low pressure, for example at the pressure at for water, ice, heat addition goes to the ice pass directly from the solid phase to the vapor phase. In the process known as sublimation. Further heat transfer resulting in superheating of the vapor. And finally another example, ice from an initial pressure of ice P at the and T ice. Through heat transfer, let the temperature increase until it reaches to centigrade. At this point, however, further heat transfer may cause some of the ice to become vapor and some to become liquid. For at this point, it is possible to have the three phases in equilibrium. This point is called the triple point. Heat addition goes to further heat transfer may cause some of the ice to become vapor and some to become liquid. For at this point, it is possible to have the three phases in equilibrium. To have three phase at equilibrium. This point is called the triple point. Defined as the state in which all three phases may be presented in equilibrium. The pressure and temperature at triple point for a number of substances are tabulated in this table. For hydrogen, triple point and oxygen, nitrogen, carbon dioxide, mercury, water, zinc, silver, copper. This whole matter is best summarized in the picture here. This whole matter is best summarized in this picture, which shows how the solid, liquid, and vapor phase may exist together in the equilibrium at triple point here. Along the sublimation line, this line, dimension, the solid and vapor phase are in equilibrium. Solid and vapor along the fusion line, the solid and liquid phase are in equilibrium. And along the vaporization line, we have the liquid and vapor phase are in equilibrium. Liquid and vapor phase are in equilibrium. The only point at which all three phases may exist in equilibrium is the triple point. This point as shown here. This is sublimation line, vaporization line, and fusion line. The vaporization line ends at the critical point because there is no distinct change from the liquid phase to the vapor phase above this critical point. Consider a solid state in A as shown in this picture. This line, this point, when the temperature increases but the pressure is constant, the substance passes directly from the solid to the vapor phase along the constant pressure line EF. For example here, the substance passes from the solid to liquid phase at the one temperature, and then from the liquid to the vapor phase at a higher temperature. The constant pressure line CD passes through the triple point, and it is only at the triple point that the three phases may exist sharp together in equilibrium. At a pressure above the critical pressure, such as GH point, there is no sharp distinction between the liquid and vapor phase. Although we have made these comments with specific reference to water, all pure substances exhibit the same general behavior. However, the triple point temperature and critical temperature vary greatly from one substance to another. For example, the critical temperature of helium in the table is about 5 degrees, therefore the absolute temperature of helium at ambient condition is over 50 times greater than the critical temperature. In contrast, water has a critical temperature of 374, and at ambient condition the temperature of water is less than half the critical temperature. Most metals have a much higher critical temperature than water. When we consider the behavior of a substance in a given state, it is often helpful to think of these states in relation to the critical states or triple point. For example, if the pressure is greater than critical pressure, it is possible to have a liquid phase and a vapor phase is in equilibrium. Or consider another example, the states at which vacuum melting. So, if the pressure is greater than the critical pressure, we can write pressure, critical pressure, we have impossible to have a liquid phase. And a vapor phase is in equilibrium. Or to consider another example, at the state that the vacuum melting is given metal is possible can be ascertained by a consideration of the properties at the triple point. Iron at a pressure just above 5 Pascal would melt at a temperature of 1535 degrees, the triple point temperature of. There is various examples. For example, this picture shows the carbon dioxide three-phase diagram. Three-phase diagram for carbon dioxide, in which it is seen that is the triple point pressure is greater than the normal atmosphere pressure. Which is very unusual. Therefore, the commonly observed phase transition under conditions of atmosphere pressure above about 100 kPa is a sublimation for solid directed to vapor, without passing through a liquid phase, which is why solid carbon dioxide is commonly referred as a dry ice. Dry ice. In this case, the commonly observed phase transition under condition of atmosphere for carbon dioxide, we have the directly gas, directly sublimation to vapor, we note that this phase transmission at 100 kPa, this point, at a temperature below 20 degrees. Finally, it should be pointed out the pure substance can exist a number of different solid phases. A transition from one solid phase to another is called the allotropic transformation. A pure substance can exist in a number of different solid phases. different solid phase. A transition from one solid phase to another is called an allotropic transformation. This figure shows a number of solid phases for water. A pure substance can have a number of triple points. But only one triple point has a solid, liquid, and vapor equilibrium. Other triple points for a pure substance can have two solid phases and a liquid phase, two solid phases and a vapor phase, or three solid phases. This is the end of this section, which is an important section in the chapter 3.